Okay, hello. One more example problem. This is another partial fractions problem. Here we have a rational expression. The degree of the numerator is 2 and the degree of the denominator is 3. So like the previous problem we did, this has a linear factor and it also has a quadratic factor. But this quadratic factor is a little bit different than the other one we looked at because it's in fact like a perfect square. So it's the square of a linear factor, you might say. Okay, so how are we going to deal with this? Well, it's going to turn out that there's going to be a special method to deal with this. But in order to try to understand this special method, let's first treat this problem exactly the way we treated the other problem. In other words, let's break this up into some thing over x minus 2 plus something over x squared minus 2x plus 1. In other words, let's ignore the fact that this is a perfect square trinomial and just treat it like it's any other quadratic. Great. If we do that, then what do we do next? Well, once again, this is a proper rational function because the degree of the numerator is less than the degree of the denominator. So therefore, no polynomial long division is possible. Therefore, no polynomial long division can be possible for either of these also. In other words, the degree of the numerator must be less than the degree of the denominator. This is a degree 1 polynomial, so this numerator must be degree 0. Or in other words, it must be a number. And over here, we have to allow for the fact that this could be a linear function. All we can say for sure is that the degree of this numerator will be less than the degree of the denominator. Okay, so with this kind of setup, we can now just do the problem. So let's do it pretty quickly. And for my students who are watching, this is the problem we started with like 2 minutes left in class. So I'm going to now multiply through both sides by x minus 1 squared x minus 2. And this we will multiply through by x minus 1 squared x minus 2, the whole entire right side. Okay, and all right, if we do that, then we get x squared minus 4x plus 6 equals, and here we get a x minus 1 squared plus bx plus c x minus 2. Okay, and now I have a single equation with 3 unknowns, and so we need to find out what a, b, and c are. So I have a quadratic on the left, I have a quadratic on the right. Do I have enough information to solve for a, b, and c? Yes, I do. And the long way to do this would be to multiply everything out on the right-hand side, collect all the like terms, and we would have a system of 3 equations in 3 variables, one for the coefficient of the quadratic, one for the linear coefficient, and one for the constant term. But instead, we will do this the fast way, and the fast way says that these 2 polynomials have to agree on all values of x. So in particular, they must agree when x is 2. So set x equal to 2 in the left polynomial, and you get 4 plus 6 is 10 minus 8 is 2. And if you set x equal to 2 in the polynomial on the right, then this entire term dies because that's 0, and we end up with just a. Okay, so already I have figured out what a is. All right, and now there's a bunch of different things to do. One thing potentially to do right now is look at the quadratic term. So I think this ends up being kind of a little bit easier. So the quadratic term on the left has a coefficient 1. And the quadratic term on the right, I think it's pretty easy, even without multiplying this whole entire thing out, to realize that if you multiplied it out, you would get only 2 quadratic terms. You're going to get an x squared over here, which is going to get multiplied by a, and the only other way to get a degree 2 term is when bx gets multiplied by x. And so this ends up being a plus b. Okay, so since a is 2, then I learned that b is negative 1. Okay, so boom, boom, and finally, maybe we can plug in x equals 0. Maybe that's a good idea. If I plug in x equals 0 on the left, then I get 6. And if I plug in x equals 0 on the right, let's see. If I plug in 0 here, that gives me a. And if I plug in 0 here and here, that ends up being c times negative 2. So minus 2c. All right, we already said that a was 2. And so 2c must be negative 4, and so C is -2. Okay, so that was pretty straightforward, and what we end up with is our conclusion is that the answer is 2 over x minus 2 plus b is -1, so that's negative x, and c is -2, so negative x minus 2 over x minus 1 squared. Okay, and seemingly, you know, the problem is over or something like that, but unfortunately, now let me just rewrite this answer. Here's what we have. X squared minus 4x plus 6 over x minus 1 squared x minus 2 equals 2 over x minus 2 plus negative x minus 2 over x minus 1 squared. Okay, let me just change the frame to make sure that we see what's going on. Okay, so great. We have our answer, and we're all done. But unfortunately, we're not done. And I'm going to put a box around this, and I want to stress that this is, you know, not wrong. I'll even go so far as to say this is correct. All the mathematical logic we followed is all legitimate. However, when it comes to actually asking what partial fractions really is, what is the whole point of the method of partial fractions? The point of the method of partial fractions is to break things up. We have complicated expressions, and we want to break them up into many, many little pieces. And to break things up into as many little pieces kind of as possible. And this, in particular, this term right here is not broken up as much as it could be. And we can see that by analyzing it a little bit further. So rewrite this negative x minus 2 as negative x minus 2 over x minus 1 over x minus 1. Put a plus here. Okay, that's like a little bit, maybe you might say, of a strange thing to do. Okay, what are the advantages of doing this? Well, I can now take this numerator and realize that degree 1 on the top, degree 1 on the bottom, I can do polynomial long division. So let's do the polynomial long division right now. I have negative x minus 2 divided by x minus 1. And so that's going to go in minus 1 times, and that gives me negative x plus 1. And when I subtract, I get negative 1 minus 1 is negative 3. Okay, so put like a box around this because that was kind of a side calculation. What have I just learned? I've just learned that this thing in the numerator here can be re-expressed as negative 1 minus 3 over x minus 1. And that whole thing is over x minus 1. Okay, so just to kind of clarify, the claim here I'm making is that the two things in the red parentheses are equal to each other. And of course they are. Just see the polynomial long division. Okay, well, having done that, now I see that this numerator can be split up into two different pieces. And so what we actually have is 2 over x minus 2 minus 1 over x minus 1 minus 3 over x minus 1 squared. Whoa. And this is better, I claim. Okay, so first of all, I will also put a box around this one, and let's just agree that this is also correct. So both of these two things are correct. This one, though not wrong, doesn't make me happy because it's not divided up as much as possible. Whereas this one makes me very happy because it is divided up as much as possible. And the thing to appreciate is, well, first of all, you have to just trust me or something that this is better. And second of all, you have to understand that based on this process, this thing that just happened is always going to happen. Because there was this perfect square trinomial, this so-called repeated linear factor here, then it's always possible to do polynomial long division with one of those x minus 1s and break it up into sort of two pieces. And these two numbers, this negative 1 and this negative 3, are going to end up being the numerators for x minus 1 and for x minus 1 squared. And since I like this better, in the future, when presented with the same problem, I am going to take a different approach. The different approach I'm going to take is to anticipate this result and therefore set up the problem to reflect that. All right. I think I gotta finish this video in like 1 minute, but what I'm now going to do in the future is to set the problem up. This is just more efficient this way, to have something over x minus 2 plus something over x minus 1 plus something over x minus 1 squared. And all of the books will tell you that those numerators should be like a, b, and c. They're going to be numbers, and the explanation, the best explanation for this is to see the thing that just happened. Okay, and think of this as just more efficient than what we did before, because we know this is going to happen, so let's just set the problem up this way. Okay, now I'm going to just do this in 1 minute. Of course, if I multiply through by those denominators, then I get a x minus 1 squared plus b x minus 1 x minus 2 plus c x minus 2. I think I did that correctly. And now it should be pretty easy to plug in x equals 2. If I do that, then once again I'm going to get 10 minus 8 is 2 equals a, so I know that a is 2. Then I can plug when x is 1, perhaps I can plug that in. If I plug 1 over here, I get 7 minus 4 is 3. When I plug 1 over here, all of that dies and I get negative c, so c is negative 3. And maybe finally I can try when x is 0, I'm going to get 6 on the left, and on the right, actually 0 is not the fastest way, but too late, I'll get a, negative 1 times negative 2 is 2, so plus 2b, and here I'll get negative 2c. But since a is 2 and c is negative 3, that becomes plus 6. And if I did this correctly, the 6's cancel, and 2b is negative 2, so b is negative 1. And this is exactly what I got a minute ago when I did it the long way. Okay, hopefully that helped. Goodbye. Just confirm that those are the same answer that we got when we did it the other way. Good.